afternoon, everybody. It's my pleasure to host today's seminar given by Navi from AMD. So I did a quick search online, again, borrowed many of the pictures from AMD website. I think this is a kind of a snapshot of what AMD is providing solutions to many industries. So you probably know that AMD used to fabricate chips, but now AMD is a fabless company that design many different types of chips for servers, for GPUs, and also DPU. I had a very nice conversation this morning with Navi, and then he essentially educated me on what is a DPU. And there are many industries that are using the solutions provided by AMD. And without further ado, I'm giving you Naveen from AMD, and he actually is a Purdue alumni, and he just graduated 2 years ago, and happened to be a TA as well for one of our TAs. So that's a very interesting coincidence. And without further ado, I'll give you Naveen, and he will talk about his experience at the AMD and sharing with you many of the useful tips. Naveen.
All right, can everyone hear me? Cool, all right. Hi everyone, my name is Naveen Navek. I am currently a product development engineer at Advanced Micro Devices, commonly known as AMD. And today I'm gonna be talking about data science in the semiconductor industry. So here's a quick preview on what we're gonna be talking about today. I'm gonna be going over what is AMD, who am I, give you guys a little bit of context on what we're gonna be talking about today. And then after that, I'm gonna go briefly into data science and yield engineering. I'll cover what the word yield means in further slides. And then I'm going to cover what career opportunities AMD has and why you'd want to work at AMD, and then some Q&A at the end. Cool. So what is AMD? So AMD is a high-performance and adaptive computing leader. What that basically means is that we make processes fast. So all of you guys are familiar with what software is, right? So software is you write lines of code and you make it do a certain operation. However, what people don't think about is hardware, which is you have the software that can run really fast. However, you need to make sure you have the hardware to support this fast software, right? And so that's what AMD specializes in. We have 27,000 employees across the world. The majority of our concentration is in the US and Canada. We have some stuff in Asia as well. And our goal is to build the best, and our goal is to change the planet in as many ways as we possibly can. So here's a list, basically a snapshot of all of the products that we make. Pretty much whatever device you're using, chances are there's probably some AMD component in it in your day-to-day life. An example is, how many people here own a PS5 or an Xbox? Raise your hands. Congratulations, all of you guys helped pay my salary. So AMD makes CPUs, we make GPUs. A CPU is a central processing unit, that's sort of the heart of a computer. A GPU helps do machine learning processes, helps run gaming engines and stuff like that. Recently, we acquired a company called Xilinx. They basically invented this thing called the FPGA, which is a field programmable gate array. It's essentially a device that you can basically reconfigure however you want, so a lot of people use it for prototyping. Because the last thing you want is to come up with a really complex design, and then all of a sudden you manufacture it, and then it doesn't work, right? So you want to make sure you test it as much as you possibly can. Cool, so who am I? All right, what do I do at AMD? So, like I said, my name is Naveen. I'm a product development engineer. That's pretty much just a generic title given to everyone in my organization, but basically I'm a data scientist. And I work in the yield engineering organization. So AMD is a company, as Professor Wu said, they don't manufacture chips. We design them and we test them, right? And because we don't manufacture them, we mostly manufacture them with TSMC, which is Taiwan Semiconductor Manufacturing Company. Because we don't manufacture them, we basically give TSMC a bunch of designs, and it goes into this black box where they manufacture it, and they give us back chips, right? And so let's say we make 100 chips with TSMC, and when we get them back, only 60 of them are working correctly. The question that we ask ourselves, what happened to the 40%? That is the only question that my entire organization is trying to solve. And this yield is essentially number of correctly functioning products divided by total number of products manufactured. So in an ideal world, your yield would be 100%. Right? But obviously you have a certain percent that's random defectivity. Maybe a particle fell on the chip. Maybe an engineer touched the chip. These are things we cannot account for, so we just account for them as random error. But my team basically figures out, are there any systematic defects happening again and again? What sort of defects are we seeing in our chips that we keep seeing on a week-to-week or a month-to-month basis? Right? And in my day-to-day work, I do yield analysis, some database infrastructure here and there, but most of my work is concentrated on model development. Okay, so what did I do at Purdue? I graduated with a Bachelor of Science in Electrical Engineering and a Bachelor of Science in Mathematics in 2022. So I've been in the industry for 2-ish years now. I was a UTA for EC 2K1, 2K7, and also CS182. I was actually an RA. Has anyone here lived at Tarkington Hall? Tark Sharks. Yeah, I was an RA there for 2 years, and I also started the EC Student Society podcast called Boiler Up, Power Down. I came up with the name. Cool, so let's go a little bit into what exactly we're going to be talking about today. So for starters, let's start really, really basic. What's a semiconductor? So the definition of the word semiconductor is something that kind of conducts electricity, right? So it doesn't have too many electrons, it doesn't have too few electrons. So silicon is an example of a semiconductor. They have 4 valence electrons, meaning you can either add or reduce electrons to make it more or less conductive, right? And so that's the building block for what's called an NPN transistor. Essentially what that is that that's basically just a device that is kind of like a resistor, but based on a supply voltage, you can change how resistive it is. So if you want, you can make it a short. If you want, you can make it an open. You can basically change how resistive it's going to be to current flowing through it. And that's the building block for the AMD Ryzen CPU. That's the building block for any chip that you see today. So that's why you usually see the word chip referred to as a semiconductor. Okay, so what's data science? The way I like to explain what data science is I like to go into what data-related careers there are and how they're different, and then I'll talk about what data science is. So there are 3 main building blocks to careers in data. The first one's a data analyst, the second one is a data engineer, and the third one is a data scientist. And a data analyst is who you want to take a look at the data first. Let's say you have a table, and let's say you want to find out, okay, how many rows do I have in this? Is this data clean? And what analysis can I do on it? So data analysts are the people who are taking a look at your data initially. They're the ones who are going to use statistical analysis software to find patterns and trends in your data. So let's say, I don't know, let's say I'm going to a restaurant. And let's say I want to find out how much money I make per week. Right? So all I do is I have a table which contains all of the transactions that happen during that week, right? And a data analyst would quickly plot a chart that sums up all of the totals across each day for a given week, right? That's what a data analyst is going to do. The second is a data engineer. A data engineer is somebody who ensures the data integrity using ETL pipelines. ETL stands for extract, transfer, and load. But basically what they do is they're the ones who are responsible for creating all of the infrastructure used to create the tables. Because you can't analyze data unless you clean it, unless you make sure it's all good, unless you make sure it exists, right? That's what a data engineer does. And last but not least, you have a data scientist. A data scientist is usually working on sort of like large-scale projects. So they're not doing day-to-day analysis, but they're working on problem statements that help the company or whatever the team is try to come to systematic conclusions faster. So they're working on statistical and machine learning algorithms, and they're also ensuring that you have proper data collection processes. Because the last thing you want is a really bad way of collecting data. Then your data is going to be slow, your data is not going to be accurate. So you want to make sure that you're accounting for that whenever you're analyzing your data, right? And so this, the table at the bottom pretty much just goes through a flow of what exactly a data scientist is going to be using on their day-to-day basis. You start off with a raw table, then you want to start pulling data. You use SQL, that stands for Structured Query Language. You use that to pull data onto your local computer or onto whatever server you're doing analysis on. Then you use Python to transform and extract this data. And then you use PyTorch, TensorFlow, whatever machine learning algorithm you want in order to start doing post-processing. This is just my personal data flow. I know a lot of engineers like to do it differently, but this is just what I use in my day-to-day work. Cool. So what does a semiconductor engineer do? This is a very, very, very complicated question. And I'm going to start with, there's no such thing as a semiconductor engineer. There are a lot of careers within the semiconductor space. So it's a huge industry. You know, you have industries like finance, healthcare, and you also have a huge industry for semiconductors, right? And so this is pretty much just a flow that describes all of the positions that are available within the semiconductor industry. Again, this is not a comprehensive list by any means. It's pretty much just when I think of a semiconductor engineer and who do I talk to, what do I think of? Right, so you start off with architecture. The way I like to think of a chip is I think about it as kind of like a building where you have a blueprint, and then after that you want to make sure you pass all regulations, then you make sure you start construction, then after that you got to make sure that after you build your building, is it feasible, right? Can people actually live there? Can people do work there? And so those are similar questions to what semiconductor engineers answer. Right, so you start off with architecture. That's the equivalent of getting a blueprint. How many rooms do you want? How many building blocks do you want? How many transistors do you want? Stuff like that. These are questions architectures are thinking about. And then after that, you have RTL design engineers. These are kind of like the civil engineer equivalent, where an RTL engineer is essentially going to be taking the blueprint and trying to see if it's feasible, if they can implement it in real life. right? This is before you produce any silicon. So all of these in the first row are pre-silicon jobs. There are basically two divisions of the silicon industry. Pre-silicon means everything that happens before manufacturing, and post-silicon is everything that happens after the chip's been manufactured. So the top row is pre-silicon. So RTL design engineers are going to be the ones writing the code. It's mostly written in this language called System Verilog. If any of you guys are interested in EC, you'll take it in this class called EC 270. At least that's what it was called when I went here. Next, you have design verification. So design verification is kind of like once you have this structure in place, once you have it simulated, does it work? So these are the people who are basically trying to break your simulation, right? So you have this code that seems to work perfectly fine, right? And now you need to make sure, are there any bugs in it? Are there any bugs that you can manually introduce? And basically a DV engineer's job is to break what the RTL engineer did, right? And then after that, you have physical design. That's when you start thinking, okay, I have a design. Okay, it seems to work fine in theory. How do I stack the layers? How do I make sure, how do I optimize for area? How do I optimize for power? How do I optimize for performance? Right? These are parameters that physical design engineers are thinking of. It's the equivalent of kind of like when you have a civil engineer, when you have an idea of how many rooms you want, how do you organize them to optimize the amount of, I guess, the amount of area or the amount of cement you want to use, right? Because all of that stuff costs money. Similarly, for a chip, each metal layer costs money. Right? And the more and more metal layers you have, the more complex your chip's going to get. So you want to make sure you minimize the amount of wires you're using in your chip. Right? Then you have manufacturing. That's, like I said, that's when you take your hands off and you're like, okay, you know what? I'm going to give it to the manufacturer. They're going to make it in the case of a fabless company. If you have a fab, like in the case of Intel, then you just give it to your fab department. They would make your chip and then they give it back to you. And then after that, you have functional testing and system testing. This is basically once you get the chip back, does it work, yes or no? Right? Functional testing checks whether or not it was manufactured correctly. So it tells you, okay, were there any metal wires that were incorrectly connected? Were there any transistors that broke? Anything like that. System testing is, can it boot the operating system? Right? Does Windows seem to work on it? Can I ship this to a customer? And then finally, you have the sales department, right? The sales department is responsible for making sure that the end customer is actually satisfied with the product. They're responsible for the pricing, other factors. And even though all of these jobs seem pretty EC heavy, there are also a lot of opportunities available for non-electrical and computer engineering majors as well. An example is supply chain and operations, right? You guys heard about the chip shortage that happened in 2021. Who did we need to fix it? Industrial engineers, right? We needed people to ensure that we were getting our chips back correctly. We needed to make sure all of our business operations were working perfectly fine and smooth. And also you have chassis design and thermals. That's just a basic example of what a mechanical engineer would do. You want to make sure that once you test your chip, once you give it to your customer, you want to make sure they don't come into any issues. They don't want wires melting, right? They don't want their power to be through the roof, right? So they want to make sure that all of those factors are optimized for as well. Cool. This is a really brief video on how exactly microchips are made. So let me go ahead.
This microchip can take up to 26 weeks to make. In its as many as 100 layers, billions of transistors are packed into an area about the size of a fingernail. They're the brains behind almost everything we use in our increasingly electronic world. Here's how these complex, tiny devices are made. The process begins with silicon-rich sand. Why silicon? Silicon is a semiconductor. It's the sweet spot between an insulator and a pure conductor. That means its properties, such as its conductivity, can be altered by adding impurities or doping to meet the needs of different electronic devices. This also allows us to control the electrical signals that pass through. Silicon is also abundant. It's one of the 10 most common elements found on Earth. But much of the silicon found in the wild is chemically bound to oxygen, so the two elements must be separated. The sand is combined with carbon and melted in crucibles to produce carbon monoxide and 99% pure silicon. After further processing, ultra-pure silicon is produced. Next, a seed crystal is placed in contact with molten silicon. As the seed crystal is slowly pulled away, silicon atoms are deposited on the bottom surface. The result is a large cylindrical boule, or a single crystal ingot of pure silicon. The boule is then thinly sliced into wafers. Silicon wafers typically have diameters of 1 to 12 inches, with the most state-of-the-art facilities being able to produce wafers up to 18 inches in diameter. Bigger wafers are, of course, able to yield more microchips. Once the silicon wafers are cut, the production process begins in full. Microchips are made in extremely sterile conditions, free from contaminants such as dust. If even just one particle of dust makes its way onto a silicon wafer, the entire batch is at risk of being ruined. This would derail a process that can take an average of 12 weeks. The first step of the production process is deposition. A thin, non-conducting layer of silicon dioxide is grown or deposited on the surface of the wafer. Then the silicon wafer is prepared for lithography by coating it with photosensitive and light-resistant materials. The next step is very critical: exposure. The prepared silicon wafers enter a lithography machine and are exposed to UV light passed through a reticle containing the chip's blueprint. The areas exposed to light are hardened, while unexposed areas are then etched away by hot gases to leave a three-dimensional microchip. The electrical conductivity of different parts of the chip can also be altered by doping them with chemicals under heat and pressure. This process can be repeated hundreds of times for the same chip, producing a more complex integrated circuit at each step. To create conducting paths between the components, a thin layer of metal, such as aluminum, is overlaid onto the chip, and the etching process is used to remove everything except the thin conducting pathways. Several layers of conductors separated by glass insulators can be laid down. Each chip on the wafer is then tested for performance before it's separated from other chips on the wafer by a saw. Since microchips are essentially circuits built on an incredibly small scale, they have a basic set of components. Capacitors can temporarily store an electrical charge. Resistors help control the electrical current. Transistors can either amplify or switch the electrical signals passing through. For more advanced chips, like those found on high-end graphics cards, there can be upwards of 28 billion transistors on board. More transistors on microchips allow them to send out more instructions, increasing the computational power. Moore's law predicts that computer chip manufacturing would advance at a steady rate, allowing transistor counts to double every 2 years. Based on the sheer power of the technology we use on a day-to-day basis, this decades-old prediction seems to still be mostly true. Manufacturers have been shrinking down their transistor sizes to fit more onto chips. Each breakthrough in transistor size has allowed the production of more powerful chips for our phones, computers, and gaming consoles. In recent years, they've gotten each transistor down to as small as 8 × 10 to the power of -8 inches in diameter, allowing an amazing 50 billion transistors to be crammed onto a single chip. Manufacturing microchips is truly one of our most complex feats, and yet innovations are happening every day.
I'm going to be honest with you guys, I actually did not watch the video until just now. So the slide where it said graphics cards, where it said NVIDIA, I wish I photoshopped AMD on top of it. That would have been really funny. All right, cool. So what's data science and yield engineering? So yield engineering, like I said before, is essentially trying to figure out what went wrong with chips, right? What went wrong? That's the only question we're trying to answer. So there are two cases whenever you manufacture a chip on a wafer. One, you cut it up, you test it, it's good. You ship it to the customer, all good, right? The other, it doesn't work. What could be the root cause? There are 3 main root causes when you're trying to find out what's wrong with a chip. 1 is a design bug. 2 is a manufacturing issue, and 3 is a testing issue. So a design bug basically means 2 wires were designed really close together, so that was resulting in them shorting, something like that. So that would be an issue where we'd relay that information back to the design team, and they would tell us, oh, let's introduce a new silicon revision. They'd give us back a newer design. We'd manufacture it. It would all be good. The second is a manufacturing defect. That means that our manufacturers had some sort of tool issue, or they changed the recipe of one of their chemicals. It basically means that the issue is not related to the chip itself, but related to the manufacturing process used to make that chip. You saw how complicated that manufacturing process was in the previous slide. There are a bunch of processes involved. So even if any one of them is tweaked slightly, it could result in gross defectivity across all of our products. And the third one is a testing issue. Basically, that means, are we testing the part incorrectly? Are we giving it too low of a voltage? Are we giving it too high of a frequency? Basically, are we excessively stressing the part? And so what a yield engineer does is that they take the failed data from the chip, they analyze it, and they generate some sort of model or some sort of visual that describes what could potentially be the root cause. A typical example would be, let's say you have a graph of the metal layer thickness for a given chip across time. And all of a sudden, as the metal layer thickness is increasing, you're seeing your yield decrease. Obviously, that's not enough to come to a conclusion, but that could be a theory that the metal thickness is actually causing your yield to decrease. Okay, so I can't talk about data science without talking about AI and machine learning. So the question is, what does AMD do in this AI and ML space? So we have two different divisions for AI. We have AI hardware and we have AI software. So as you guys know, AMD is a hardware company, so we work with AI hardware. So that basically means that even though you have an incredibly complicated machine learning algorithm that somebody's written, unless you have the hardware to run that really fast, to train that really fast, that algorithm is never going to be feasible in the real world. So you got to make sure that you're designing these custom parts, kind of like Professor Wu went over, where you have these DPUs, you have these GPUs, that essentially do specific computations for you. Because at the end of the day, all a machine learning algorithm is doing is that it's running a bunch of numbers. All it's doing is doing really, really complex linear algebra again and again until it comes to a conclusion, right? So what's the solution there? Just come up with AI hardware that just does linear algebra again and again, right? The second one, what do we do with respect to AI software? So AMD recently launched a software called ROCm. It's essentially an open source platform that you can use to communicate to a GPU. So that's really helpful because it gives the user more access to their GPU and also makes sure that they can take advantage of all of this machine learning training and also customize a lot of the parameters for the GPU to their liking, right? And also, AMD previously did not have a lot of support for TensorFlow as well as PyTorch, but that's also been increasing. Okay. So what can AMD do for you guys, right? So we have a very well-known internship program. Most of it is located in Austin, Boxborough, and Santa Clara, California. However, we do have some other locations as well. This is a photo of a bunch of interns in Lisa's. Am I in this picture? Probably not. Okay, I was remote. Sorry, never mind. Okay, cool. So what's our internship timeline? We have spring, fall, and summer internships. One of the things that I really like about AMD, which you don't see at a lot of companies, is that most companies heavily concentrate all of their internships during the summer. But AMD usually has internships going all year round. I was a co-op from May of 2021 to December of 2021. So I was a summer as well as a fall intern. And that was really nice because I feel like having 8 months gives you a lot more time to contribute towards a high value project. And it also gives you more time just in general to network within the company. And also it increases your odds of converting that to a full-time offer, right? And right now we're looking for bachelor's, master's, and PhD graduates in ECE. However, we are also looking for other related fields as well. This QR code, I believe, takes you to the AMD careers webpage, but there should be a lot of postings there available. Right now we should be starting to post for fall internships because we're getting towards the beginning of summer. But if you find anything, just apply. Whoops. Yeah. Yeah, that's pretty much all I had to go over today.
Thank you, Naveen. So I have some questions that students asked before this class. So one of the questions is related to TSMC that you mentioned at the beginning. So does being a fabless company put AMD at a disadvantage as they have to wait, or AMD have to wait to receive their products? And this is opposed to an integrated manufacturing company like Intel, that they can produce their design.
That's a really good question. So to give everyone a little bit of context, basically, AMD used to have a fab. So, AMD was started in the 60s, and we used to have a fab up until 2009. And right now, it's called Global Foundries. Basically, there were a couple of years where AMD was not doing well, the business was not doing too hot, and we basically spun off Global Foundries as an independent company. And if you look at the graph of how AMD was performing, all of a sudden, you'll see that after we spun off the company, we skyrocketed. We started doing way better. And that's not because our fab was terrible. It's because of the fact that it's because of the fact that a fabless company has advantages because a fab requires a lot of R&D resources that if you have a typical engineering company where you're focusing on design, it's difficult to split your resources to focus on design as well as manufacturing R&D. So that's why a lot of fabless companies like Apple, Qualcomm, NVIDIA, they all use TSMC. Also, TSMC is it's incredibly good at keeping up with the large volumes because they're able to handle all of these customers seamlessly, and they've been doing it for years, right? And they are incredibly ahead of the game, and that's probably the main reason why we don't have a fab.
Okay. And then another question is related to AMD's competitors. How has AMD managed to stay competitive with both Intel in the CPU space and NVIDIA in the GPU space, while other companies primarily focus on just one space?
Okay. So I think that started off with why AMD was founded. So, the founder, he had an innovation, and they were all from one of the original semiconductor companies back in California, and they started AMD, and their goal from the get-go was to create a company that could do it all, right? We wanted to create a semiconductor company that could do it all. And then when Lisa Su took over, we came up with the chiplet architecture. So to give everyone a little bit of context, chiplets are essentially just subsets of a chip. And the advantage that serves is that if you manufacture your entire chip as a single unit, even if there's one defect on that chip, your chip will not work, right? Versus if you have a chiplet architecture, if one of your chiplets has a defect, all you have to do is just use one that works, right? So this leads to a significant reduction in cost because your yield is going to be higher. And also, if you lose a component, you're only losing 1/3 of your chip as opposed to losing the entire thing. Because your defects are going to be a function of area of the silicon, right? And so that's one of the main reasons why AMD is able to compete in terms of pricing as well as performance with respect to the CPU market.
And another question is, how does AMD approach the security and reliability features in its processors, especially with increasing cybersecurity threats and data breaches?
So I don't know how much I can talk about this, but basically, again, I hope this is an industry standard, but I think basically a lot of companies, within their chips, they embed a tiny security chip. And that security chip is responsible for ensuring that when you access data, you're not accessing someone else's. Because you got to remember, a lot of our chips are used for servers, right? And what are servers used by? A bunch of people, right? They all have their separate virtual machines. They all have their separate instances. So we have a dedicated tiny chip that essentially checks your name and says, oh, Naveen's logging in. Let me only give Naveen this tiny portion of memory. Let me make sure that he cannot access anything else. And so that's the way that we handle security within our chips.
Okay. Next question is, since AMD is one of the few companies that open resources its graphics car drivers, has AMD ever taken inspiration from the community and officially implemented these improvements?
Yeah, so our ROCm is an open source repository, as you guys know. Basically, you can just go into GitHub and you can file an open issue, and then you can have somebody take a look at it and they can implement it. So that's very much a feasible option, yeah.
So I have one last question. For students interested in pursuing careers in AI chip design, what skills and expertise do you recommend developing? Does AMD have any opportunities for those passionate about this field?
So from what I've observed, most of the people who are in AI chip design are usually hardware engineers, so they're chip designers by trade, but they have a very, very good understanding of machine learning. Because at the end of the day, if you're a chip designer, you're a chip designer, right? So you got to make sure you understand, okay, what exactly what's an ALU, right? What cache coherence protocol am I using? You got to make sure you understand the building blocks in order to make a chip. Then after that, you have to understand, okay, when a machine learning model is using my chip, what components are getting used most? Right? Which parts of the chip are spiking in terms of activity. And you want to make sure you incorporate more of those. You want to make sure you account for all the bottlenecks. But at the end of the day, an AI chip designer is a chip designer who has a very, very good understanding of machine learning models.
Thank you. Yep. Now we want to open the questions to the classroom.
You mentioned the general cycle of the yield engineer of you design the chips, you make the chips, you get them, and then you go and look and say, hey, what's wrong with this?
Yeah.
You also mentioned how the chip making cycles can be incredibly long. I think the video mentioned that it can be like 22 weeks or almost half a year in some cases. How does that affect your job of that you can't really make any changes except twice a year?
So that's a really good question. So in that video, 22 weeks is definitely not accurate. It's definitely way, way shorter than 22 weeks. So you're right, we do have to account for long turnover time though. So what we do is that basically when we're initially making a product, we want to make sure that cycle's a lot quicker. So we put a lot more pressure on our manufacturers to make sure that when we initially get silicon, that cycle's really, really low. So a lot of these yield engineers, a lot of the debug they're doing is the first couple weeks. During the first couple weeks, we ship all of the chips to the US, we do all the testing here, so that way we don't have to wait for our results to come in late. But during the initial cycle of the chip, that turnover time is a lot smaller, but once it gets more and more stable, we allow that turnover time to get longer because at that point, we've already caught all of the really strong systematic signals. And at that point, it's just like one-off systematic signals. Like, okay, they had a tool change, which we can identify pretty quickly.
How long is a standard? Do you know how long is a standard chip design during the early phases?
During the early phase, if I had to guess, probably like a month, maybe.
Okay.
Probably less. Yeah.
As like a young employee at like such a huge company with so many engineers, I guess how do you feel like your input like in a team is heard throughout I guess your peers, and do you feel like you I guess are able to like make inputs on these huge projects?
It's a really good question. So one of the things that you'll observe, and this is a thing throughout the entire semiconductor industry, everyone's either really young or really old. And that's because the market was doing pretty badly during this couple of decades. So there are a lot of people who are in their 40s and 50s, and there are a lot of people in their 20s, but there are not a lot of people in their 30s. And so that serves a really nice advantage because I feel like it's easy to make friends because there are a lot of people in their 20s, but I also feel like it's really easy to learn because there are a lot of people who've been in the industry 10, 20. My manager's been in the industry for 37 years. So I feel like it's really, really easy to learn. And I feel like it's also really nice to contribute because all of these engineers are acknowledging the fact that eventually they're all going to retire, right? Who's the next generation? So they want to make sure that they're giving us all of the resources and giving us all the training to make sure that we are a really, really good next generation engineer. Yeah, what's up?
I'm just curious, what are like the downsides of having a chiplet design? Like, is it slower than using a single chip?
Yes. So, one of the main disadvantages to a chiplet architecture is the fact that in a single, they're called monolithic die. That basically means the entire thing's made on one particular chip. If it's all made on the same, you don't have to worry about the lag between communication within the chip. It's all going to be the same speed. Versus if you're doing a chiplet architecture, you have to worry about the speed of the packaging that you install. You now have to worry about the communication that's happening between die and die. So yeah, you do make a slight performance sacrifice, but if you make enough optimizations to your communication bus, then the performance will be significantly higher. But yeah, in theory, if you had a monolithic die versus a chiplet architecture die, and both of them had the exact same specs, the monolithic die would perform better, yeah.
So I have one question. Maybe I asked you like several times today, but can you share a bit more about like how you find your offers or internship at AMD and how you decided to pursue your full-time career in AMD after?
Yeah, of course. So I started at Purdue in fall of 2018. During September of 2019, which was my sophomore year of college, I went to the Industrial Roundtable, IR, and I met with AMD. And I met with an engineer who went to Purdue, and she liked my resume, she liked the conversation we had. I ended up sending her an email. I did not hear back that year. However, the next year when I met with another AMD representative, I decided to email my the one that I was talking to before, from the year before, and she emailed me back saying, hey, there's actually an opening on my team, would you like to interview? And then I interviewed, and then they liked me. I got an offer, and I got a full-time offer, and I just stuck with it.
And why did you decide to pursue a full-time at AMD?
So I interned
What kind of things do you like about AMD?
Oh, yeah. So I think one of the greatest things about AMD is the fact that everyone is approachable. I feel like when you're young, everyone is taught that people are either intelligent or approachable. And I think AMD is proof that that's wrong. There are so many people who are really, really smart, but also love teaching. I think that's one of the greatest things about the company is that for an early engineer starting their career, I think it's a really, really fun place to just go and learn and just absorb the information around you. My manager always says, your first 3 years in the industry, you are nothing but a sponge. You're supposed to absorb everything around you.
And then one more question from IR, because all the students will attend IR hopefully like every year. So what's your tips about approaching to those employers? Hey, how do you do to like make yourself stand out?
I think one of the main things is obviously be sure you know everything on your resume. I think a lot of the times when you're talking to somebody, a lot of people are going to ask you specifics to your resume, so be sure you talk to them. But probably the best piece of advice I have is that not only should they see you as an intelligent engineer, they should also see you as a cool person. I think in general, honestly, all recruiters want and all people want is a good conversation. I think that'll take you a really, really long way.